Okay, let us begin. Today's next speaker is Wenqi K from Minnesota, and she's going to talk about the role of Curvaton in the post-Planck era.
Yeah, thanks. Thank the organizer for the invitation. Today I'm going to talk about the constraints on the Curvaton model, which is incorporated into the inflaton model facing the Planck 2018 constraints. Sorry, can move on. Oh, yeah, it's okay. Just a brief outline. In first part, I'm going to talk very briefly about the single field inflation and its status after the release of Planck 2018 measurements. And then I move on to curvatons, in giving simple definitions of curvaton and how does a curvaton resurrect dead models. Because a curvaton generates curvature perturbations, which alters the CMB observables, and it is crucial to use that point to change the CMB observables and resurrect dead models. And in the third part, I'm going to talk about our work where we constrain the curvaton parameter space when it is incorporated into the single field inflation model facing the Planck 2018 measurements. And finally, I will summarize. So let's start. I guess you know the interest of inflationary theory. It solves the horizon problem, flatness problem, generates density fluctuations, and so on. And in the textbook treatment, you always define those several parameters given by the first and second derivatives of the inflaton potential. They are called epsilon and eta, respectively. And from the given inflaton potential, you can also derive different cosmological observables, including the scalar power spectrum amplitude, the scalar spectral index NS, tensor to scalar ratio R, and non-Gaussianity. So here, when you see those indices star, I mean evaluating all those values at the CMB pivot scale K star. And in this talk, I'm going to focus on the simplest inflation theory, the single field inflation, where it is driven by a single inflaton field. So for now, everything is textbook treatment. And if you wonder what kind of inflation models we have, I give you here the example reference published 10 years ago. And in this reference, people centralized the existing known inflation models, and already looking at the table of content, it is impressive to see the number and the variety of ways to realize inflation. You can have multiple field inflation, you can have many parameters controlling inflation, and I'm sure that since 10 years, there are many more models that are updated. So among all those various models, how to distinguish inflation models experimentally, the most standard way is to look at the CMB observables that they predict. Different inflation models can give different NSR or AS values, and then you can put them in different categories. However, there are also scenarios where two different inflation models give very close predictions of NS and R. This is, for example, the case for Starobinsky model and alpha tractor T models. They give very almost degenerate NS and R. And in that case, we have found that the primordial gravitational waves can allow you to distinguish these observables, and they have actually very distinct spectra. But this is not the focus of our talk. And this being said, how do we select those viable models among the whole set of inflation models? And the authority to answer this question is the Planck 2018 results and combined with BICEP KEK 2021. So here is the plot from the BICEP KK paper where they give the combined constraint of NS and R in this blue circle, and you also have those theory predictions that lie sometimes outside the constraints. The combined result of Planck and bicep KK give you a pretty stringent upper bound on the tensor to scalar ratio around 0.036. And in the future CMB experiments, we also expect to have an even more improved upper bound on the tensor to scalar ratio. And typically this is case with Simon's observatory. And also the combined result gives you the spectral index, which has to lie in this interval. And also Planck has given a pretty precise value for this amplitude AS. And this amplitude will allow you to fix the scale of inflation. And Planck has also given this value for the FNL non-Gaussianity, but non-Gaussianity still has a pretty large error bar. As you can see, non-Gaussianity of order 100 has been excluded, but you can still possibly have a order 1 non-Gaussianity, as it is possible to have 0 non-Gaussianity. So for now, it is not sure. And as a result, the Planck and bicep KK results have many implications on the existing inflation models. Roughly speaking, they can be divided into two categories. You have the single field inflation models that are currently excluded or disfavored, and those that still survive the Planck constraints. And among the excluded models, you have the monomial quartic potential, which is also known as the chaotic inflation. This model gives you a tensor to scalar ratio, which is gigantic and is clearly ruled out. And you also have the example of natural inflation introduced more than 20 years ago, inspired by axial models. And this model also gives you a spectral index, which is too low. And another example is the new inflation model, which also gives rise to this spectral index way too small. So all those models are excluded or disfavored. And these are just some examples. There are many more. And for the models that still survive, you have the famous Starobinsky model, which can be derived from R plus R squared. And you also have the alpha attractor T models. Both models can also be well incorporated into a good UV theory, like no-scale supergravity. So they are well motivated and still agree very well. Here I extract this plot from the 2021 paper where people analyzed the viability of Starobinsky and T models facing the new Planck bicep KK constraints. In the dark blue circles, you have the combined experimental constraints on NS and R. And in the red and yellow shaded regions, you have the Starobinsky and T model predictions. So you can see that for now, they are still very safe. And so after Planck and bicep KK, you're now facing this cosmological graveyard with all those single field inflation models ruled out because they always have inconsistent NS and or R. And you always can find a way to save them. And today I'm going to talk about the Curvaton. The Curvaton can change the initial single field inflation predictions, and potentially it can move those predictions back to the CMB constraints. So what is a curvaton? Briefly speaking, the curvaton is defined as a spectator scalar. So its coupling to the inflaton can be negligible during inflation. And it is also a light scalar compared to the Hubble scale of inflation. And this point is important for the curvaton to have large quantum fluctuations during inflation, and consequently, it will have an energy density initially. And finally, very importantly, the curvaton has to decay after inflation, because if it is a stable scalar, then it will survive until today to be a dark matter candidate, and this is another thing, and this is not a curvaton. So the curvaton has to decay after inflation, and that contributes to the radiation bath. The curvaton is basically given by these 3 points. The introduction of the curvaton is not artificial at all, and actually there exists many BSM models that can very well incorporate such decaying scalar. And for example, in the 2000s, people have already realized that the superstring moduli can play the role of a curvaton. At that time, it wasn't called Curvaton, but such moduli fields can actually change the CMB observables, and that's the role that Curvaton can play. So now let's look at simply the life of a curvaton. As I mentioned before, during inflation, the curvaton can go through quantum fluctuations. Those fluctuations will reach this asymptotic value given below. And you can see that in the denominator, you have the mass of the curvaton, and the mass of the curvaton is very small. And as a result, the asymptotic value will be much larger than the Hubble scale at the end of inflation. As a result, at the end of inflation, you have a non-vanishing energy density of the curvaton, which then will play the role to alter the observables. And then if you look at this plot for curvaton energy density, you can see that its energy density will stay frozen for a while after inflation due to Hubble friction. And at some moment, the Hubble parameter will become comparable to the curvaton mass, and around that moment, the oscillations will start. We also assume that the curvaton has a quadratic potential, so it behaves like a matter, and its energy density will then decrease during oscillations as a to power minus 3. Then at another later moment, the Hubble parameter will become comparable to the curvaton decay rate. And around that moment, the curvaton decays will happen and its energy density will decrease exponentially. And very importantly, during inflation, the curvatons will recover isocurvature perturbations, and these isocurvature perturbations during the decays will be transferred to curvature perturbations, which in turn affect the CMB observables, and that's the key point of this talk. And let's look more in detail on how the curvaton affects those CMB observables. In the first place, we can look at the spectral index and tensor to scalar ratio. And the curvaton effect basically depends on its energy density compared to the radiation at the moment of the decay. And then we introduce this ratio X of the energy density of the curvaton over the energy density of the radiation. And in the literature, people also frequently use this other parameter, Rchi, which is simply a redefinition of X. So you can use either of them. And secondly, the effect of the curvaton also depends on its contribution to the power spectrum. So one introduces this other parameter of the curvaton contribution to the power spectrum over the total power spectrum P zeta. And you can see that this omega chi parameter also depends on Rchi, the ratio of energy densities. It depends also on the mass of the curvaton and the Hubble scale at the end of inflation. Then from these parameters, you can derive the new spectral index and tensor to scalar ratio. I won't go into details about the derivation. If you're interested, you can find, for example, in this reference. And here I only give the final result. The new spectral index and tensor to scalar ratio in the presence of curvaton are written here. Here, the N star and R star are defined as the spectral index and tensor to scalar ratio in the absence of curvaton. And in the red boxes, you then have the curvaton contributions. You can see that the spectral index is shifted by the presence of a curvaton, and this shift is proportional to the curvaton contribution to the power spectrum omega chi, as well as those slow roll parameters in the parentheses. The slow roll parameters with star indices are those from the inflaton, and eta chi is the slow roll parameter from the curvaton. And secondly, the tensor to scalar ratio is modified by this rescaling factor 1 minus omega chi. Since omega chi is smaller than 1, larger than 0, this rescaling is then smaller than 0. And as a result, the tensor to scalar ratio is always reduced by the curvaton. And on the other hand, another famous effect of the curvaton is to generate non-Gaussianity. Let's recall the current status of non-Gaussianity. In experiments, Planck 2018 has given this constraint on the non-Gaussianity, which can be 0 or order 1, and we still don't know. And for the series size, the single field inflation model predicts generically a value of non-Gaussianity, which is very close to 0. So for now, theory and experiment are still compatible. But what if in the future, if we look into the future prospects, if the future experiment has improved the sensibility, and we will be able to tell the absence or not of non-Gaussianity, then we are facing the situation that if there's still no Gaussianity detected, then single field inflation is still safe. If, however, we find in the future a clear signal of non-Gaussianity, then it has many profound implications on inflation models and probably can indicate the presence of multi-field inflation. And in particular, the single field inflation alone will be in trouble. And actually, early on, more than 20 years ago, people have realized that a scalar like a Curvaton, which is unstable and light, can generate primordial non-Gaussianity. And this then will come to save the single field inflation model in the second situation. And here again, I won't show the detailed derivation. I give directly the final result of the non-Gaussianity from the Curvaton. And this is again expressed in terms of the previous two parameters, R chi and omega chi. More precisely, this non-Gaussianity from the Curvaton can be 0 for some specific value of R chi. It can also be positive or negative. So there are many possible values of non-Gaussianity from the Curvaton. And then there is a special limit that is interesting. In the limit of Curvaton domination, the Curvaton energy density over the radiation energy density goes to infinity, and the Curvaton is entirely responsible for the curvature perturbation. In that case, you recover this special value of FNO, which is -5/4 that you can find very often in the literature. So in summary, what does the Curvaton do? The Curvaton can generate non-Gaussianity. It can also have parameters which have a 0 non-Gaussianity. The Curvaton also reduces all the time the tensor to scalar ratio. It can lower the tensor to scalar ratio back to the required constraint. And furthermore, the Curvaton also shifts the spectral index. From the second and third points, you can see that you can use the Curvaton to resurrect the dead models which are incompatible with NS and R constraints. Sometimes in the literature, people also call such a Curvaton savior Curvaton because it saves dead models. Now let's look at the status of the Curvaton facing Planck, which is our work. So in our work, the key questions we have asked are, and we have answered are, given an inflation model in conjunction with the Planck constraints combined with bicep KK, if the inflation model is compatible with Planck, then if there exists a Curvaton field in such a model, how do we keep the model compatible? How to not shift away NS and R out of the constraints. And if, however, the inflation model is incompatible with Planck, then if there is a Curvaton in the model, how does the Curvaton save the model, and what's the parameter space to do that? And to look at this problem, we can remember again the life of a Curvaton, but now in the context of a cosmological history. And there are basically three parameters controlling the whole story. The parameters are the mass of the Curvaton, the decay rate, and the reheating temperature, T reheating, which depends on the inflaton decay rate. And then there are four key moments in its life. You have the end of inflation given by the scale factor E end. You have the onset of oscillations defined by the Hubble parameter being comparable with to the inflaton mass, the curvaton mass, and onset of decays when the Hubble parameter is comparable to the curvaton decay rate. And finally, you have the moment of reheating. A reheating here is defined as a moment where the inflaton energy density is equal to the radiation energy density. And sometimes I will call this the end of reheating, because after this moment, A reheating, the energy density of the inflaton will decrease exponentially, and that will signal the end of reheating. And so following these 4 key moments, you then have 3 logical possibilities in our study, depending on where you place the end of reheating inside the life of a curvaton. So the first possibility is that the reheating happens after the curvaton oscillates and after the curvaton decays. But this first possibility is not so interesting because all the curvaton has already decayed before the radiation bath is generated. So the effect of the curvaton is almost invisible, and curvaton is subdominant in this scenario. However, we also have case 2 and case 3 defined as reheating happening either between oscillations and decays or happening before oscillations and decays. In case 2 and case 3, you can have important contributions from the curvaton. And so now we have 3 cases. Which case are we in? Actually, we are given 3 parameters: T reheating, decay rate, and mass. Given those 3 parameters, you can actually uniquely pin down which case we are in. And we can further distinguish subcases where the curvaton either decays at a matter or radiation-dominated era. In the case where the curvaton decays in the matter-dominated era, since there is also a presence of radiation bath, this will be a second matter-dominated era, by the way. So now we can use some simple analytical expressions to derive the boundaries of those different cases and subcases. Here, I just show the example of case 2 RD, just to see how it works. Case 2 RD is defined as the reheating happening between oscillations and decays, and since it is radiation dominated, the ratio of energy densities X will be smaller than 1. We define the moment of oscillation more precisely as m chi equals to 3/2 h, and the Freeman equation before the oscillations is dominated by the inflaton energy density. So we have this relation for the Hubble parameter. And since we assume that the inflaton behaves like matter, it will decrease with a to the power 3, and that will then lead to the ratio between a chi and a end, depending on the mass of curvaton. And we ask this to be larger than 1, and that gives an inequality for the mass of the curvaton. Then if you look at a later moment after reheating, since the universe is radiation dominated, the radiation redshifts as a to the power 4, we then have this relation for the Hubble parameter, which then finally leads to another ratio a d chi over a end, and its inequality then gives us a relation for the decay rate and reheating temperature. If we look more specifically at the moment of decay, we can derive the energy densities. The energy density for the curvaton is simply 1/2 m squared chi squared, since we assume it to be quadratic, and then plus with this redshift factor. And this gives us the curvaton decay, the curvaton energy density at the decay in this tedious formula. And on the other hand, we can also get the radiation energy density at the decay depending on the curvaton decay rate. And with these quantities, we can derive the analytical expression for the ratio X, which is given here. And you remember that all the new CMB observables will depend on X and omega chi. We can then use this analytical formula to derive CMB observables for any reheating temperature, mass, and decay rate, and for any inflation models. So in summary, the condition for case 2 RD is given in the first line and second line. The first line is a definition of case 2, and second line is a definition of a subcase RD. So, so all the decay rates and masses of the curvaton in this region will lie in case 2 RD. So similarly, we can derive the conditions for all other cases and subcases, so we can uniquely find which case we are in. And most importantly, I want to mention that for each case, we have analytical expressions of X and also for omega chi to get the CMB observables NS and R and non-Gaussianity. And for now, the discussion is model independent, just assuming that the curvaton is quadratic. And this can be applied to any models. And that's what we are going to do next. We are going to look at two specific examples. The first example is the new inflation model, which was excluded because its NS prediction was too small. However, the tensor to scalar ratio from new inflation is very, very tiny, so it's still okay with the current constraint. And our question is, what are the parameters of the curvaton, M chi and gamma chi, to save the new inflation model? On the other hand, we also looked at this Starobinsky model, which has a compatible NS and R predictions. And in this case, our question is, what are the parameters of a curvaton to not ruin the model if you have a Starobinsky plus curvaton? And by this, I mean we want to keep NS within 2 sigma deviations. And before looking at the curvaton, let's have a look more precisely on the prediction minus measurement when there's no curvaton. So in this plot, you have the difference between theory and experiment for both models. And the bands mean the plus minus 2 sigma deviation. So if you have the band lying around delta ns equals to 0, it means that the theory agrees with experiments within 2 sigma. So here clearly you can see that for a large range of T reheating, the Starobinsky model agrees very well with the experiment. However, the new inflation model is always below delta ns equals to 0, no matter the reasonable reheating temperature. And so the curvaton clearly can do something to move these bands. To see more precisely, let's pick up again this previous formula. In the red box, you have the curvaton contribution, and actually for both models, the curvaton contribution is positive. And namely, graphically, the curvaton will move up all those bands, and eventually it moves up those bands back to 0. So we want to more precisely move up the new inflation band for different reheating temperatures to delta ns equals 0, and we don't want to move up too much the band for Starobinsky. And how much can the curvaton do to move up those bands? And let's pick up again this formula, and let's call this curvaton part little delta ns. And we can plot little delta ns versus m chi or gamma chi for Starobinsky model, for example. Since we have the analytical expressions, we can clearly do that. So on the left-hand side, you have the dependence on the mass of the curvaton for different reheating temperatures. So you see clearly that it is possible to have a sizable contribution to the spectral index. And for some parameters, for large mass of the curvaton and large reheating temperature, it can even go up to order 10. So the curvaton can clearly do something. And on the other hand, we can also see that the larger, the smaller than the decay rate is, the larger the contribution will be. Basically, if you have small decay rates, the curvaton will decay even later, which has more contribution to the final perturbations. And also we have to be sure that while the curvaton can save the model, it shouldn't give a too large non-Gaussianity out of the current bounds. And we can pick up again the non-Gaussianities from the curvaton. And remember that the non-Gaussianity can be positive or negative or can be 0. And we can, since we have the analytical expressions, we can plot FNL in terms of the mass of or decay rates. And here you see that again, the Curvaton can generate very large non-Gaussianities. So we really have to pay attention to how much non-Gaussianities we have. And in particular, those vertical lines correspond to the solutions to FNL equals to 0. And also for certain mass ranges and T reheatings, or the gamma or the decay rate, you can have even order 100 and order 1,000 non-Gaussianities. So that's a thing that we need to pay attention to while solving the models. So now I'm going to show the results. We start with the new inflation model that is saved by the Curvaton, and below are the plots for the parameter space of the Curvaton mass versus decay rate. Just a simple explanation for the color codes. The unshaded regions are the excluded regions, and shaded regions with different colors are the case 2 and case 3 with RD or MD. Another explanation for the legends, those dashed and solid purple green lines correspond to the different solutions in the parameter space for different values of FNL. So it can range from -11 to 9. It also has 0 solutions. And finally, the most important part of these plots are these narrow gray bands. These gray bands are precisely the solutions of the Curvaton, so that NS of new inflation agrees with the experiments with 2 sigma. Or put in another way, in the gray bands, the Curvaton saves new inflation. So if we combine the gray bands and those solid dashed lines, we can see that there are parts of the parameter space which have correct NS with regard to experiments and large FNL. So in particular, in this red star, you have FNL equals to 9, while guaranteeing a good agreement of new inflation. And of course, you can also have this intersection where NS agrees with experiments and there is no non-Gaussianity. So there are many possibilities for non-Gaussianity while guaranteeing the correct NS. And now let's go to Star-Robinsky model. Here, our goal is different. We don't want to ruin Star-Robinsky model. And Star-Robinsky model doesn't need to be saved. The color codes are still the same. You have excluded regions in white and colored regions for the case 2 and case 3. So here we also have the same lines for different solutions to FNL from -11 to 9, same color code. And in particular, we have this new region in Star-Robinsky 10 to 13 GeV. This black shaded region is the region that is excluded due to excess of entropy production. So this is another thing that we need to worry about when the Curvaton mass is too low and its decay rate is too low. It will generate too much entropy production, which dilutes too much the baryon symmetry. So this is the region that is excluded due to entropy. And again, you have the same gray bands, but now the gray bands are not the only parameters that are allowed. Actually, the whole region on the left and upper region for with regard to the gray bands are allowed for NS. Because if you have a lower mass or a higher decay rates, a higher mass or higher decay rates, you have lower contributions from the Curvaton, so it's still okay. So all the gray shaded regions are allowed. And similarly as before, you have those intersections of different values of FNL. You can have correct NS while generating large non-Gaussianity, or you can have 0 non-Gaussianity from the Curvaton. So again, many possibilities. And we also have looked at another example, which is the monomial potential. We remember that in the new inflation case, the tensor to scalar ratio was compatible, but its prediction of NS was wrong, so it was saved by the Curvaton. Actually, there are also examples where the tensor to scalar ratio is also wrong, and we want to know if the Curvaton can also do something to save the model. So let's look at this famous example of quartic potential or chaotic inflation. Its prediction of tensor to scalar ratio is gigantic and even almost 10 times higher than the upper bound. And also its NS is also wrong. Both are ruled out. This cannot be said by increasing the e-folds. Actually, even if you go up to 444 e-folds, you can indeed lower the tensor to scalar ratio to 0.036, but then you will in turn higher the NS, which is way too large. So quartic potential alone cannot solve the problem. And the question is, can we use the curvaton to solve the problem? And the short answer is yes. We can introduce a curvaton to the quartic potential because the curvaton always lower the tensor to scalar ratio, and there actually exists the parameters for the curvaton that lowers the tensor to scalar ratio back to 0.036. And we tested some parameters, and they are all reasonable. And typically for T reheating equals to 10 to the 5 GeV, the spectral index will be brought back to 0.959, which lies in the required interval. The tensor to scalar ratio of the curvaton, the tensor to scalar ratio is lowered by the curvaton back to 0.036, around 51 e-folds. So all those numbers agree with the experiment, and the curvaton mass is low. Its decay rate is also reasonable. So we can see that the curvaton can also save the quartic potential. Then we can ask another question: what's the situation for the quadratic potential? The quadratic potential is in the same situation. It predicts a gigantic tensor to scalar ratio, and we want to study the curvaton parameter space. And just a quick inspection has told us that curvaton will work only for the T reheating as low as 7 MeV, but it's close to violating the BBN bound. So it's more complicated to save the quadratic potential using the curvaton. Now let's come to the summary. Here we have seen that the curvaton can generate curvature perturbations, which in turn affect CMB observables. We can use this characteristic to change the predictions for certain single field inflation models. And in some cases, previously ruled out single field inflation can be saved by the curvaton. And in our study, we have derived analytical expressions for the ratio x as well as omega chi to evaluate the new CMB observables. And this study is mostly model independent and can be applied to many models. As we have seen, we have studied quartic and quadratic potentials using those expressions. For the new inflation case, we have found a narrow region of M chi and gamma chi, which resurrects the model facing Planck data. So it was previously ruled out. It is now back to life thanks to curvaton. And also a side note is that among the parameters in the curvaton that resurrects the model, there are parameters that gives you large non-Gaussianities possible that are possible while satisfying those NS and R constraints. And it is also possible to have zero non-Gaussianity while satisfying NS and R. So there is a big room for the freedom. And also, as I noted, it is straightforward to apply this prescription to other models, as we have seen in the quartic cases. We just need to apply those analytical expressions. And finally, when it comes to existence or not of the curvaton, even though the curvaton is a well-motivated scalar that exists in many BSM models, and whether it exists or not will then depend on the better precision in future experiments on NSR or FNL. And the existence of a curvaton will also in particular depend on the absence or not of non-Gaussianity, and a determination of non-Gaussianity will then lead to an indicator of the possible existence of the curvaton. And this being said, thank you very much for